Welcome to today's webinar. The topic today is using Python console in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR. I'm for example responsible for the German and English webinars, the technical content of the website, newsletter, and so on. I will be the moderator today, and I will answer your questions during the webinar. Rebecca Goebel will do the presentation. She's responsible for product engineering and customer support in the product engineering for instance, for the web service and API. Okay, then I say something how you can ask questions. At first, I switch off my camera that you can see the full screen. You can press that button here, then enter your question in this field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that should be all from my side. I hand over to Rebecca. Rebecca, it's your turn.
Thank you, Andreas, for the introduction. I'm very happy to show you the Python console in this webinar today. And first of all, I will tell you something about in-app scripting and the console. Afterwards, I will point out the difference between web service and the Python console. Next, I will show you a new functionality of RFEM 6, which is the model export as Python script. And in the end, I will show you two examples as a live demonstration about how to use the Python console. But first of all, what is in-app scripting and what is the console? With RFEM 6 and RStab 9, it became possible to directly run scripts inside the program and modify the structure. In-app scripting was already possible using JavaScript since a long time, as some of you might already have noticed, but now we also implemented the in-app scripting for Python. With in-app scripting, you can, for example, parameterize your models or automate some tasks, and of course, you can also retrieve information from the model. The scripts can be saved locally, but you can also manage them using the script manager in RFEM. We are offering some example scripts, but you can also add several of your own scripts to the script manager. In the script manager, you can switch between JavaScript and Python, as Python is now also possible to use. The console, on the other hand, allows the direct interaction with RFEM via single commands. With the console, you can also create geometry objects and load cases, settings and loads, but you can there also read out information from the model. And moreover, it's possible to use external libraries in the console. An additional tool of the console is the info box. You can find it at the top of the console, and it contains all available objects and the corresponding parameters. I think this is a very helpful tool, especially when you start using the console, because you can simply look up what object you want to define and see all available parameters, and also how it can be changed in the console. Another new tool is the command prompt button. By clicking the black button, the Windows CMD will open, and there you can install external libraries, like for example Pandas or Plotly, in the console. You can install these packages in the same way as you would do it in Visual Studio Code, for example, and afterwards you can use the whole functionality of these libraries inside the console. But I will show you both functionalities later in the demonstration part. Now I would like to point out the differences between web service and the Python console. Web services are a type of application programming interface where we use an XML-based information exchange, and our web service offers certain functions to communicate with RFEM in the programming languages C#, Python, and JavaScript. The communication with RFEM happens via a server, and therefore an internet connection is needed to use the web service. The console, on the other hand, is embedded into RFEM and therefore allows a direct communication with RFEM. That means that it can be used without internet connection. The syntax of the Python console is slightly different from our Python high-level functions, but don't worry, the functions are also pretty easy anyway, and you can adapt to it very fast. Another advantage of the console is that no programming environment, such as, for example, Visual Studio Code, is needed. Because of that, I think it can be a good start to programming also for beginners. Okay, then I would switch, I would first show you the export as Python script, which is a new functionality of RFEM that is available since RFEM version 6.07.0009, which was released last week. With this new function, you can import and export Python scripts. So you can, for example, create your RFEM model and afterwards export the model as a Python script and see all the commands that are necessary to create the structure using the Python console or the Python script manager. So it can be very useful to start with programming in the console or the script manager because you see how the objects can be created. And you can also import a Python script and use this to create a new model. Okay, but that's it from that part. I would like to jump to the demonstration part now. And first of all, I would like to show you how you can display the console and the script manager in RFEM. So the console, it's already displayed here, but you can turn it on and off with this button. And here at the top you have the switch to switch between the programming languages JavaScript and Python. Next to it there's a button to open the info box where you can find all the objects. For example, we can take a look into nodes and we see all available properties for nodes. And if we choose one of these properties, for example no, we see here the description, that it's the object number, and at the bottom we also see how we have to define it in the console to change this property. And we can also click OK here, and the command is automatically transferred to the console and we can just edit it and use it. On the right side there's the CMD button, which opens a Windows CMD window, and as you can see the RFEM folder is already inside this window, so we can just enter the command to install some external libraries. It's the same command as you would use in Visual Studio Code. For example, I want to install the library Plotly, so I write pip install and afterwards the name of the library, which is Plotly. Press enter and then the library either gets installed or you get a message like me that this library is already installed on, and I can just use it. Okay, the script manager can be displayed using this button. And here you can also switch between JavaScript and Python. At the top you see your user scripts and at the bottom you see some examples that you can just use. Okay, but we want to focus on the console today, so I will turn the script manager off for now and start with the first example. In the first example, I want to create a single span beam, and therefore I already created an empty model that I can start from scratch. First of all, I want to create a node. I use the function nodes.create, and now I leave the parenthesis empty because that creates a node at the coordinate origin at 0, 0, 0. This is the standard setting, so that's why you don't need to pass any parameters. But for the second node, which should be in a distance of 4 meters from the first node, I need to hand over some parameters and also need a different function. Here I use the function nodes.createStandard, which is the function to create a standard node, and I pass in the node number 2, the x coordinate, y and z coordinate, and press enter, and we see that the node already has been created. Afterwards, I would like to define a material, so I say materials.create, and inside the brackets I specify the material number, it's number 1, and I also have to pass the material name, which should be S235 steel. The material name is equivalent to the material names in the material library, so if you are not sure what the exact name of your material is, you can just look it up in the material library and copy that name to use it in the Python console. And when I press enter, we see that the material has been created. Afterwards, I will create a section for my member. Here I use the command sections.create, and I say it's section number 1 again. Then I have to define the material of the section, the material equals, and then I have to define the material number as a string. I want to use material number 1 for my section. And lastly, I have to give the name of the section. I want to use an IPE 200 section. And again, this is the name of the section is the same name as it is in the section library. Okay, and we see the section has been created as we wish. Okay, now in the next step, in order to later create a member, I first have to create a line. And I do this by using the command lines.createPolyline. It's line number 1 again, and as a second parameter, I have to pass in the nodes of the line as a string, comma-separated string. Okay. And now we can create a member of type beam. For members, there are specific functions for each type of member. So the function to create a beam is members.createBeam, and I pass in the number of the beam, number 1, then the line on which the beam should be, line 1, and also the section that the member should have. When I press enter, I see the beam has been created. In the next step, I want to create two different types of nodal supports. The first nodal support is created by using nodal supports.create, and in the parentheses I hand over the number of the nodal support 1, afterwards the nodes on which the nodal support should be applied. It's only node 1 in my example, and the next parameter is the spring. It contains all spring constants for the nodal support. I want it to be rigid in all three directions, so I hand over inf in a list. And for the rotation, I define the parameter rotational restraint and also hand over a list. And here I want it to be rigid around the x and z axis, but free around the y axis. Okay. I press enter and the nodal support has been created and already applied to node number 1. Now for the second nodal support, I don't have to type everything again. I can just use my arrow keys of the keyboard, and when I press the upper arrow, I see the previous command that I used, and I can also switch between some of the prior commands. And this makes it much easier because I can just modify this command and change the number of the nodal support, the nodes, and also this rotational restraint value. Press enter and I have created my second nodal support very fast. Now in the next step I want to add another node to the member, which should be at a distance of 1 meter, 1.5 meters from the first node. And because I don't want the member to be divided, I want to create a node of type onMember. As it was already the same for members, there are also different functions for each type of node. So now we are not going to use nodes.create standard, but nodes.create onMember. And here we enter again the number of the node, number 3, but we don't have to pass in some coordinates, but instead we define the distance of the node from the start. And if you maybe don't know what's the exact name of this parameter, we can now use the info box. Then we search for nodes and search for the correct parameter, which is in this case distance from start absolute. We can copy it here and paste it into our function and set it to 1.5 meters. Press enter and the node of type onMember has already been created. Next, I will define static analysis settings. I use static analysis settings.create, and here I can just pass in the number and don't have to do any other settings, because this will just create the standard configuration of the static analysis settings, which is fine for this example. Oh, this was the stability analysis settings, but I wanted to create the static analysis settings. Okay. Now the static analysis settings have been created, and we can now create a load case. I want to create a load case for self-weight and use the command loadcases.create. I pass in the number of the load case, number 1, next the name, self-weight, and as third parameter I have to define the static analysis settings, and it's defined by the name of the static analysis settings here, which is SA1. You can also see this down here. Okay, when I press enter, we see that we have now one load case in our model. So now in the next step I can create some loads. First of all, I want to create a continuous member load and apply it to the beam. To do that, I first need to define in which load case the load should be applied. It's load case number 1. And then I say member loads, because I want to apply a member load in this case, and dot create force. It's the type of load that should be applied. Then I pass in the number of the load 1, then the member on which the load should be. It's member number 1. And lastly, I will define the magnitude of the load, which should be 3000 Newton per meter. For the loads, it's important that you have to pass the magnitude values in SI units, so you have to use Newton and meters. This will create a load of 3 kilonewton per meter on the beam. And we can see that it was successful and can jump to the next load. In the next step, I want to create a nodal load on this node on member that we created. So I define the load case of the load again, load case 1. Say dot nodal loads in this case, and dot create force. It's force number 1. It should be applied on node number 3. The magnitude should be 5000 Newton, which is equivalent to 5 kilonewton. And I can also define the load direction, which is W in this case. Okay, and the load has been created. So now my model is ready. I created every object that I need, but we could also change some parameters. We can not only create parameters using the Python console, but we can also change some objects. So for example, I now want to change the location of this node on member, and especially to change some properties, it's very useful to use this info box here. I can go to nodes again. I already know that the parameter name is distance from start absolute. So I click here, see how it can be changed, and now I can click on OK, and the command is in the console. In the brackets behind nodes, I have to define what node I want to modify. It's node number 3, and after the dot, I specify the property that I want to change. And I can set this now to 3 meters and press enter, and we see that the node and the nodal load have been moved along the beam. Another change that I could make now is to change the rotation of the member. To do so, I take a look into the info box again, go to members and search for the right property. In this case, it's rotation angle. I press OK and get the command in the console. Then I enter member number 1 in the brackets and specify the rotation angle. For the rotation angle, it's important to specify it in radians, which is in my case 1.57 radians, which is equivalent to 90 degrees. I press enter and we see that the member has been rotated now. Okay, that's it for the first example. So I will just switch quickly to the second example. Here I also already created an empty model. In the second example, I want to create a steel frame with bracing. And because it's a new model and a new example, I want to clear the console. We can do this by using the command clr. And we can start with a fresh empty console. In the beginning, I create a standard node again at the coordinate origin at 0, 0, 0, as we did in the first example. Afterwards, I will create the remaining nodes using the command nodes.createStandard, as we did in the first example already. It's node number 2 and it's located at 0, 0 and -5. Okay, for the third node I will use my upper arrow key again, that I don't have to type the whole command again. I just changed the node number to 3, the x coordinate to 4, can press enter and I have my node. I do the same for node number 4. And here it's also possible to leave some parameters empty for y and z coordinates, because this node should be located at location 4, 0, 0, and if the coordinates are 0, you can leave them empty because it's automatically applied. Okay. In the next step, I will create my material. I use the command materials.create. It's material number 1, and this time I will use a steel S355. Press enter. Okay. And in the next step, I will create 2 different types of sections. So I want to use one section for the frame and another type of section for the bracings. So for the first section, I use the command sections.create. I pass in again the number of the section, afterwards the material as string, material number 1, and lastly the name of the section, and here I want to use an HEA 200. Okay, and for the bracings I want to use another section. It's section number 2. The material is material number 1 again, and the name of the section is R14. Okay, and we see both sections have been successfully created. Now I will create the lines as preparation to later create the members. So I use the command lines.create polyline again and pass in the nodes as comma separated string. Okay. By using my arrow keys, I can do this pretty quickly. It's now line number 2 and nodes 3 and 4. Okay. So the last line is at nodes 2 and 3. Okay, now we have created all our lines and we can start to create the members. First, I will create all the members of type beam by using the command members.create beam. And the first beam has number 1. And now I don't have to specify any other property like the line number or something, or the section, because the first member should be located on line number 1 and it should also use section number 1. So I don't have to specify these because it's the default setting. But I want to define another parameter because I want to rotate the member around 90 degrees. So I define the rotation angle and set it to 1.57 radians. And we see the member was created and it's also already rotated around 90 degrees. I do the same for the second member. I have to change the member number, but here I also have to define the line on which the member should be, because it's not line 1 anymore, but line 2. Okay, so now I have to create both my columns, and now I will create the upper beam. It's located on line 5, and this time I don't have to use the rotation angle. Yeah, I can just click enter and our frame is ready. Now I will create the bracings. For the bracings I want to use members of type tension, so we have another function for these type of member. So we use members.create tension and we pass in the number of the beam, the line, and the section. This time we have to specify the section because it's not section 1 but section 2. Oh, okay, I have a small typo here. I need to use the dot, of course. Okay, and now it works. So I will now create a second tension member also. It's member number 5 on line number 4. Okay. In the next step I will again create 2 nodal supports. These are the same nodal supports as I used in the first example. So the first nodal support should be rigid around the x-axis also, but free around the y-axis. Okay. And yeah, it's also very helpful that we have these error messages directly in the console, which can help you to find the reason for your errors. So in my case, it was this parenthesis that was too much. Now it's working. Okay, and for the second nodal support, number 2 on node number 4. And it's free around the x-axis. Okay. Now our geometry is ready. And in the next step I can create my static analysis settings, but here I want to do a special setting. So I'm first going to show you the settings in the GUI. So I create a new static analysis settings, and because I have these members of type tension, I want to use the special setting exceptional handling, failing members to be removed individually. And I also need to use this setting when I create the static analysis settings via the console. So we use static analysis settings.create again, pass over the number of the settings, and now we need an additional parameter to define the exceptional handling. So we can look into the console and into the info box again and search for the right parameter, which is this one, exceptional handling enabled. I copy the name and paste it into my function and set it to true, which is enabling the checkbox. Okay, we created it and we can check if it's right. And we see, yes, the checkbox is active and we have this option enabled. After that, I will now create a load case for self-weight. First, I need to use the command load cases.create. It's load case number 1. The name is self-weight again. And the static analysis settings are of name SA1. Okay. And now, as a last step, I will create a member load that should be applied on the beam on top of the frame. And to do that, I first specify the load case in which the load should be applied. It's load case 1. I say .member loads because I want to apply a member load, and say .create force. It should be applied on member number 3, which is this one, and the magnitude should be 3 kilonewton per meter. Okay, and I can check and see the load has been applied correctly. Okay, so that's it also for the second example. Our model is finally created, and now we could calculate it manually via the GUI, for example, and analyze the structure. As the last example, I would like to show you the Python import and export function. Therefore, I will open a more complex model. It's a concrete structure that contains nodes, members, and also surfaces, openings, and some loads. So it also has several load cases. Yeah, and now I can export this structure to a Python script via File, Export, Python script. Then I save it. And I can, when I now open this Python script, I can check, for example, how the nodes were created. I see how thicknesses can be created, how the surfaces and openings are created. And this could be very helpful if I want to create my own script that contains surfaces, for example. But I could now also import this Python script to create a new structure. So I will use File, Import Python script. I choose my concrete Python script and open this. And it will create a new RFEM file now, and it contains the whole concrete structure. It also contains now all load cases and also the loads. Yeah, so you can see it's pretty easy. It's very fast to create a model using this import function. But you could also use a different way to create the structure using the Python script. So you could also copy the whole script here and go to the console. I will first delete everything from this model and now paste the whole code into the Python console. So it's all the lines now in the Python console. And then I can press enter and see that the structure was also created really quick. And the third way to create the structure would be to use the script concrete.py and save it in the folder of the user scripts, and then I could always, when I open RFEM, start my concrete script and create this structure. Okay, so that's it for the demonstration part. I hope you could get a first sight of how the Python console is used and about the advantages of it. And now I'm giving the word back to Andreas.
Thank you, Rebecca, for your presentation. I have an additional hint. Just use our free online services, such as the Geozone tool. Only a few clicks are for free, but you can buy click packages on our website in the web shop. You can use the free online tool to determine cross-section properties. Then we have an FAQ and knowledge base, database, a lot of articles that help you for your daily work. Then you can download models from our website as examples for your projects. You can ask Mia, our chatbot, all the time. Just use the free online tools. Okay, that should be also all from my side. Thank you for your attention. Thanks to Rebecca for the presentation. I wish all a nice rest of the day. Bye-bye.